Hello everyone, we are starting the 7th session of a video series on the subject nanoelectronics, and in this session we shall discuss yet another effect of magnetic field on nanostructures. In the previous session we discussed the Aharonov-Bohm effect, where we found that in nanostructures the magnetic field created an oscillation, which was a kind of a magnetized oscillation, right? So now we shall discuss about the Shubnikov-de Haas effect, or we can call it the SDH effect. Well, this defines the magnetic field effect on the electrical as well as the transport properties of a two-dimensional system. So if Aharonov-Bohm effect was on the magnetization type of oscillation, here we are discussing the electrical type of oscillation or the effect of magnetic field on the electrical properties of a two-dimensional system. Well, the oscillation in the material's conductivity, basically they occur at low temperature, and if it is in the presence of a very high magnetic field, you call such an effect as the SDH effect or Shubnikov-de Haas effect. So when the oscillation is at lower temperature and very intense magnetic field, you call this the SDH effect. Now when your temperature is extremely low and your magnetic field extremely high, what happens is the free electrons present in the conduction band, they behave as simple oscillators or simple harmonic oscillators, similar to our previous session. We have seen this in the previous session, right? That is one property that magnetic field basically exerts on any kind of crystal. So that's what happens here. When your temperature is low and your magnetic field extremely high, the electrons in the conduction band, they behave as simple harmonic oscillators. They keep oscillating. If the magnetic field is changed, the oscillation period also changes, and the resulting energy levels, they generate the Landau energy levels. So according to each magnetic field, there is different speed of oscillation which generate different energy levels. And in each Landau levels, the energy and the number of electron state can increase only with increasing magnetic field. So as magnetic field increases, the number of electrons and their energy increases in each Landau level. Thus, as magnetic field increases, our Landau level also moves on to higher energy levels. When these energy level, so we are talking about energy levels E1, E2, E3, E4, those sub bands of energies. When these energy levels, say an energy level passes E1, consider energy level E1. Suppose this energy level E1 passes the Fermi level. What happens is this energy level loses its electrons or depopulates it, and these electrons are now free to conduct, or these electrons now flow as current. This causes our electrons to oscillate periodically and produces a measurable oscillation in the material's conductivity. So if whenever your energy level, say En, passes your Fermi level, the energy level will lose its electrons, will make their electrons free, so that now the electrons flow as current, and this causes periodic oscillations, because at times the electrons are captured in the energy levels. Once it crosses the Fermi level, they flow. So this continuous motion generates periodic oscillations. Now as you vary the magnetic field B, now as the intensity of your magnetic field is varied, the energy and degeneracy of the Landau level also changes. So see, this is pretty evident because the energy, degeneracy, all these depends upon the magnetic field. So whenever there is a change in your magnetic field, these parameters also changes. We have just seen that as magnetic field increases, the levels energy as well as the number of electrons also increases. So this is pretty clear. So in most of the condition, what happens is the density of state for a two-dimensional system is tried to be maintained a constant even when there is a effect in magnetic field. We have seen that we cannot make it precisely the constant, right? We have seen the change that happens in the DOS function of a two-dimensional system. There was a broadening in the peaks. So yet we tried to maintain this energy level constant in the DOS of a two-dimensional system. But as B increases, the Landau levels moves higher and higher up in the energy because these separations are quantized, right? So each energy level is a multiple of h omega c, and the degeneracy also increases. As the energy level increases, degeneracy also increases. The filling factor in each energy level is defined by this equation V. It's nothing but your density of state divided by D. Now what is the significance of this filling factor? Basically the filling factor V is not an integer. But at 0 Kelvin, say suppose the value of V is 5.3. What does it indicate? The maximum integer number less than V, that is less than 5.3, maximum integer number is 5. This indicates that there is 5 Landau levels which are occupied. If V is not an integer, the maximum integer less than V. If it is 5.3, the maximum integer less than V is 5, which indicate there is 5 Landau levels which are already occupied. Now if your filling factor V is an integer, says the number of V, the value of V is 5. It indicates that all your Landau levels are occupied. Okay? If V is not an integer, the maximum integer less than V indicates the number of occupied Landau levels. And if V is an integer, it indicates that all your Landau levels are occupied. And if V is a integer, then its Fermi level will lie between the Landau levels, and small change in energy will not affect the DOS function at this condition. Now if V is a fraction, is say n plus or minus 0.5, which means it is not a perfect integer, then the DOS shows maxima, and EF have the Fermi level will have values of energy at the peak values because the DOS shows a maximum. So when the filling factor is an integer, your Fermi level lies between your Landau levels, and the DOS function is not changed much. However, if your filling factor is not an integer, the DOS will show a maximum value, and as well as your Fermi level will have values at peak energies. Now here consider a two-dimensional structure. So we have two potential probes. So across these two probes, we are taking the potential difference. From this probe, we shall take the Hall voltage. Across the gate, you are applying the gate voltage. And this graph shows the variation of gate voltage with respect to the potential difference between this probe, which I represent this as UPP. There is two probes. The potential difference between this probe is UPP. And this Hall voltage is UH. So I am taking a plot of the gate voltage across my Hall voltage and the potential difference between the probe. So what I am doing is I am just studying the effect of my SDH effect on a two-dimensional structure. So what is observable? We can see that there is continuous oscillations. So this is your UPP, potential difference between the probes, and this is your Hall voltage. So in UPP we can see continuous oscillations. So why is this so? So we can see that this oscillation is due to our SDH effect, where your voltage drop, see this voltage drop is proportional to the resistivity of your material. And the oscillation produced by SDH in 2D system depends only on the component of your magnetic field, which is perpendicular to your interface. It just considers the magnetic field component which is perpendicular to your interface. Others doesn't have a role in the SDH effect. So we have seen that SDH effect, they mainly are oscillation which controls the electrical behavior, the resistivity, electrical behavior as well as the transport properties of nanostructures. Whereas the Aharonov-Bohm effect, those are oscillation generated due to magnetization. I hope these are clear. You may also go through your notes so that you can relate it and you can understand the concept a bit more well. If there is any doubt, please let me know. Thank you.